viscosity is something, kinematic viscosity. It's a diffusivity of momentum, and as any diffusivity, it's some typical velocity times typical mean free path. And so we say, well, okay, let's say that the typical velocity is the same v, and the typical mean free path, like I mentally imagine that there are vortices, and the largest vortex will be like this. So I put it like this instead of this. And I multiplied it by v divided by h squared, and I say that this is sg alpha. And so I've got my v squared g alpha h. And then if you put here 10 to 3 centimeters per square second, and alpha you put like 10 minus 4 for a riva, and h you put 10 to 3, which is 10 meters, centimeters, then you get kind of something like 1 meter per second, which is what we expect from any river to be. Well, that's bullshit, right? I mean, it's not a derivation, not anything. It's just, trying to guess how we would get a reasonable answer. I mean, like, you're a physicist, an engineer come to you, and you want to get money for consulting, so he asks you what you expect to be the answer, you give this answer, right? You get your consulting money, and then you start asking, what the hell, I mean, where it comes from. And first thing that if you're a physicist, now, at some moment I try to comment you how physicist, engineer, and mathematician look at turbulence. There are 3 different perspectives. So now I'm in between physics and engineer. At some other, I'll try to get on the other side. So first of all, as you're a physicist, you start thinking in terms of symmetries. That's the way physicists think, right? And first symmetry which always come to mind is like time reversibility. If you look at this equation, this is time reversible. What does it mean? You change t to minus t and v to minus v, and it keeps its form, right? See, t to minus t, v to minus v is the same. V to minus v is the same. P is quadratic in v, as we discussed. So without this term, it's beautiful, right? So what this term does, it breaks time reversibility because it's friction, right? And we really expect here friction, something which is a resistance. And resistance is something which stops the fluid. Now, we get an answer, there is no new. This factor tells you what are actually your molecular degrees of freedom, which really brings irreversibility. Irreversibility comes from molecular degrees of freedom, right? So what we're now dealing with is what is called anomaly. Let me write it over there because we're still a long way from it. At the end of the 4th lecture, we'll more or less understand what it's all about. It's a very fashionable term now in quantum field theory and in condensed matter. An anomaly means following, that you have a symmetry. Then you introduce something which breaks this symmetry, a symmetry breaking factor. In our case, it's nu. In quantum, it could be h bar. By the way, h bar is also, if you look at Schrödinger equation, it's a factor in front of a highest derivative, like our new Laplace. They only have it with I. So it's many things you can understand in quantum anomalies and in dissipative anomalies, just saying, okay, they are just like us, but imaginary. So what is anomaly is you say that when I'm introducing a symmetry breaking factor, I have an effect of symmetry breaking. Let's say it dissipates. Something not conserved. And then you shrink to 0 your symmetry breaking factor, and effect of symmetry breaking has a finite limit. That's called anomaly. Okay? So in a sense, what I was trying to bullshit my way into a true estimate, it's still wrong, by the way, but it's now wrong only logarithmically, which will be on the 4th lecture, right? But order of magnitude, it's already okay. I'm trying to do anomaly. I'm trying to say that somehow, when nu is so small, it's important that it's there, but the answer does not depend on its magnitude. And now what we'll be doing, starting from this lecture, next one, we'll start to see how it's actually possible. What fluid must do so that effect of a very, very small factor would be finite and have a finite limit when this factor goes to 0, to plus 0, as mathematicians would say. Okay? So do we know any simple example of it? One-dimensional. Like one-dimensional flow. Could one-dimensional flow do something like this? Has an anomaly. Burgers. Yeah, sure. Of course. Well, Burgers is, I intentionally write it like this. You watch science, because I always forget which is, okay, whatever, forcing or 0. This U is not this V. Excellent. Okay, this U, by the way, is not this V, because how you get Burgers out of this, you need to consider it compressible. You need to add another equation. Let's make it one-dimensional. You need to assume that your rho is 1 plus delta rho. You need to assume that your delta P is C squared delta rho. That's a derivative of pressure with respect to density. It's now finite. Then you get in a linear approximation this equation, and there will be nonlinear terms. Then you say that this is actually can be written as dx minus dt times d1 over dt minus dx, 1 over c dt plus dx. You have waves running in one direction and another direction. It's a second order equation, as we discussed. Compressibility means you are back to second order in time. And then you say, okay, let's consider waves only running in one direction, go into the reference frame moving with c, and then you get Burgers equation. You can find in the book all the derivation. And incidentally, this u is not this v, it's renormalized. Yeah. It's not a Riemann wave, because a Riemann wave is inherently nonlinear. This is a perturbation expansion over V over C. Okay? And that's how you get Burgers. Okay? And this U, incidentally, is V1 plus gamma over 2, where gamma is P rho over gamma, adiabaticity coefficient. I'm not doing it. This is really elementary. You probably did it. Okay. So now, if you look at Burgers, first of all, it was already Berenger shown you in the lecture that you have a trivial solution of it. Let's look for u, which is a function of x minus wt, just running wave, right? So if it's like this, then this ut is just minus vwx, right? So it's only depends on the running coordinate. Now, this is derivative, this is derivative, this is derivative, so you can integrate, you get minus w u plus u squared over 2 minus nu ux equal to some constant, right? And then this is the first order equation. I integrate it once over x, right? So this may give me u. This is d dx of u squared over 2, this u squared over 2. I integrated this, it gave me this. Okay? Yeah, I really want you to follow. I'm doing only elementary calculations, right? I mean, nothing fancy. No path integrals. Good. Now this is the first order, so you can just integrate it. So let me write you a solution. U is 2w 1 plus c, whatever it is, the c, it's an exponent x minus wt over nu. Good. Incidentally, it looks like this. So if you look at its asymptotics, it's 2w over here, right? When this exponent could be neglected. And then it goes to 0 exponentially here, but the front moves with the velocity w, which is half of this. Is it clear why it moves with the speed, which is half of the velocity behind the front? such things must be intuitive, right? What is essentially compressible flow, right? It's a momentum conservation. This is just a momentum conservation. It tells you that you have a fluid which is at rest here and fluid which moves behind. So what happens here is that the fluid particle from behind hit the standing fluid particle, stick together, and continue together. Then it's clear why they continue with half speed, right? Now notice what happened here. That you have a trajectories. This was a standing particle, this was fluid, that was moving, and then was slowly coming and then moving together. So you have trajectories in xt plane, like characteristic crossing. And then they go together. We'll return to it later. Afterwards, it's totally elementary, right? Now, if you would be interested in the energy dissipation rate by this equation, what's your energy? Your energy is u squared. Well, over 2. Does not matter. So if you would be interested in d dt of u squared, just take this equation, as Vlad shown you very, very clearly in a much more sophisticated way of how you actually do such things. But this is a truly elementary part. So let me get back to my ut. So I multiplied it by u and integrate over space. So this term would disappear, right? And here what I will get, I will integrate it by parts. So what I will get is that this is minus nu integral du dx squared over dx. What you now do, you take this, you plug it here. What you get? Would the answer depend on nu? Do this exercise, okay? So what you find out that as nu going to 0, you find nu over here, right? So as nu going to 0, this getting sharper and sharper, and of course the factor in front going to 0, right? But then it's also the integration region in which you have du dx different from 0 shrinks. But du dx itself is 1 over nu squared. So this would give you nu, this would give you nu, this would give you 1 over nu squared. And the answer is independent on nu. You know, like I remember when I was a student and somebody, well, Mandelbrot, well, they fractals, and some physicists asked, okay, with Brownian motion, it's like a prose, it's something new, and we are speaking it all the time. So this is something which you know since undergrads, right? This is an anomaly. A dissipation rate of a Burger's shock wave is independent on viscosity. It has a finite limit where the viscosity goes to 0. Okay? Let's examine. So we've seen anomalies. We don't let this quantum field theory people scare us easily. Okay? Now, that was trivial, relatively, one-dimensional. Let's get back to our incompressible problem and try to understand how we get our anomalies and how we can get something dissipative independent on the dissipation coefficient. So what I will now do, it's a counterpart to it, which I intentionally chosen, and at the lecture number 4 we'll return and compare. And this would be a flow with not a straight lines. This is really important distinction. And you will often hear turbulence, turbulence, turbulence in this school as if there is one turbulence. What I really want you to get, at least from this set of lecture, that there are at least 2 very different turbulences with the same incompressible fluid. So what I now want to do, I want to consider a simple flow past a cylinder or sphere. Okay? So imagine that I have a flow. Asymptotics at infinity is given by a uniform flow, right? And I would like to understand what would be the flow around this sphere. right? If I would be doing it, assuming that my velocity, my viscosity is totally negligible in an ideal flow, then what I would get without this term, I would get Euler equation. And Euler equation has a beautiful property. It has a Kelvin theory. It tells you that if you defined omega, which is the curl of velocity, namely you just take this equation and you take a curl of it, so you get d omega dt, and the curl of pressure would be 0, and rho is constant. So you can write here the respective equation, and then you can show that if you now integrate this omega over any contour which is liquid and move with the fluid, then this would be 0. It's called Kelvin theory. It's pretty easy to see because you can write the integral over area as an integral over dl of v. This is the circulation of velocity is the same as the flux of curl of velocity. And when you do d dt, it's pretty easy to see that dl dt, it would be dv. V, it's a full derivative. And here would be d dl of dv dt. And then if you substitute of dv dt, this Nordlian term would also turn into 0. So what it's all about is that if you start from such a flow which evidently have 0 vorticity, just a constant flow, so its curl is 0, what ideal fluid suggests that it would be 0 vorticity everywhere. But if your omega is 0, it means that velocity is a gradient of some potential. If curl is 0, then your vector field is a gradient. And then it's very easy to solve this problem, because now if you substitute here v is a gradient of phi, and here is v is a gradient of v, it's a very easy, it's just electrostatics. That's what essentially what people did most of the 19th century. They were doing fluid mechanics, doing potential theory, which has nothing to do with real flows. And then you can find a solution, but if you are interested in what would be the force acting on this fluid, you can immediately predict that it would be 0, because again, this flow, potential flow, would have no difference between left and right. It is just dipole flow. And also, we know that without viscosity, this equation is time reversible. So you can just reverse the velocity back, and the pressure would not change. But the pressure, integral of pressure over the surface, it what gives you a force. So I'm skipping all these computations. They are kind of trivial. But you know that in the ideal flow limit, you cannot get any force acting on a body. Okay, you say then we cannot. So let's consider it with viscosity. Unfortunately, nobody can solve this equation with a sphere or cylinder in 2D. Just can't. Well, you can solve it on a computer, but it's a non-linear partial differential, even steady flow. I mean, we now consider a steady flow. And then we say, okay, then let's consider that Reynolds number, which is this u times this r divided by nu is very, very small. Then we can neglect this term, and it's a linear equation. And then again, you can actually, because it's incompressible, you take divergency of it, and this would turn into 0, no external forcing now. So it just will be Laplacian pressure equal to 0, so you need to find a solution of a Laplace equation. And again, your solution is only determined by a single quantity, which is this u. and it's a vector. So if you're looking for the solution of Laplace equation, and it's a linear equation, because now pressure and velocity related linearly, you know that pressure is just a dipole field. And I'm not writing it, it's a famous Stokes flow. At some point, I went to the library, took all the four, I guess, probably, volume of Stokes and just read everything he wrote about fluid mechanics. It took like maybe 4 hours or 5 hours. Immensely joyful experience. I very much recommend it. First of all, he's very clearly writing. Second, you see how in his PhD he makes an error. And 12 years later, he corrects it. He comes back to it. And I was actually looking for if he kind of invented something which I invented, and then I understood that he actually did. So Stokes did, by the way, both potential and this one. Okay, and then you can compute the force which act on your body. You've realized that the Stokes solution is kind of complicated. It has 1 over r part, which eventually there is a scale, let's call it RB, which is nu over u. When you're at such distance, your effective Reynolds number for the unity. So you cannot use this solution, assuming that your Reynolds is small, at a distance is larger than this, right? So there is kind of a what we call boundary layer around this, where this RB, nu over u, again, everything is determined by u. And you can compute force, which is 6 q rho nu RU. Excellent. Okay. And now you ask if this is a really force of resistance, which your body, I mean, you need to move this is with velocity u, or you need this force to keep it at place when the flow comes into it. Okay? And what I've shown you at the end of first lecture, I was showing you this force turned into what is called friction factor, which is a force divided by a dimensional estimate. You can always say that my force is my typical pressure times my typical area. Right? This is an estimate which essentially Newton made long before Stokes. He said, imagine how much momentum, if I would move my body with a radius r, with a velocity u, how much momentum I would impact into a fluid. Right? So my momentum is rho r squared u, and every second I am moving a distance u. That's how much momentum I impact. That was Newton's argument in optics, we will say. Newton is also very beautiful to read, by the way. And we have now Principia very well translated into English from Latin, right? So this was Newton's estimate for a force. So now, kind of traditionally, we measure whatever we do. So let's look at it. And what I've shown you at the end of last lecture is empirical data. And empirical data, it's a dimensionless number called friction factor. And of course, we plot it as a function of another dimensionless number, which, let me remind you, is this one, right? So at a very, very low Reynolds number, we expect Stokes law to be true, and it's true. So it's 1 over r, which means it's just proportional to the viscosity, right? And then something happens, not around 1, like around 10 to 3, whatever. It's really, and then it kind of goes like this. Then sometime around 10 to 5, it drops. A little bit recovers, and then more or less continues. This value is of order unity. It depends on a form, but for a cylinder, I don't know, like 0.8, 0.7. Okay. So, well, this is anomaly, right? Reynolds goes to infinity, nu goes to 0. Nu is the only factor which determines dissipation, friction, loss. And it tells you that at some point your answer stops depending on viscosity. Well, we understand what happens. When nu goes to 0, this boundary layer in which this viscosity is important here, right? When nu going to 0, it shrinks. When Reynolds number is very large, this boundary layer is very, very thin, like a shock front. So what is your idea? How actually we can get a finite resistance? It's called drag. Finite drag at a limit of 0 viscosity. Does it come from a small viscous boundary layer around the body exactly the way that the finite dissipation came out of a shock? Answer immediately what's your intuition tells you. And answer is yes or no? No. Somebody thinks yes? Could it be that this tiny boundary layer gives you this friction exactly the way? So you answered no. Somebody think yes? Everybody thinks no? Yes. You think yes. So you think that this can do, and you think that this cannot. Any arbiter, somebody who did not think before, no intuition, but now switch on your rationality. Let's think rationally. What is essentially this friction, this resistance? Is the rate with which you transfer momentum, right? And what actually happens when we shrink this boundary layer? Well, you know what happens physically. Yes. There is something totally unexpected. And friction, the nu goes to 0. Okay? I keep u, I keep r, friction goes to 0, nu, Reynolds goes to infinity, and some absolutely genius German in 1905 gave a talk in engineering congress, after which he was immediately appointed professor of mathematics at Göttingen, which ask any German, it's just an impossible feat if you're an engineer from a provincial school, right? So, and what was in his talk? Boundary layer, and let me tell you, fortunately, I wish I would invented this. What he told his engineering colleagues, but there were few mathematicians there, and Courant and Gilbert was so impressed that they immediately made this guy professor of at Göttingen and built a lab for him. He tells the following thing. Imagine that you are really, this is a tiny boundary layer, I don't know what is there. Just look at a fluid particle which comes to this on a central symmetry line. So if it's a little bit above, it goes up. If it's a little bit below, it goes down, right? So what is this point? It's stagnation point. What is the pressure at the stagnation point? It's a maximum or it's a minimum? Maximum. Because we have Bernoulli's theory, which is essentially conservation law. It tells you that P plus rho v squared, essentially potential energy. Remember, but this is the potential energy of interaction of fluid particles. This kinetic energy, that's constant, right? So this pressure is high. This pressure is high. So what happens to this particle? It accelerates because when it comes close to stagnation point, here the velocity is very low. Just I want you to see how totally qualitative argument by an engineer totally created new branch of mathematics. Okay, so follow me. So this fluid particle coming very close to stagnation point has a very low velocity here. And then it starts accelerating because you need to go around, right? And which means that here velocity will be maximum, so the pressure will be, which makes sense. pressure high behind, it pushes you, you accelerate, right? Good. Now, because it's so tiny boundary layer, that around it the flow is kind of almost symmetric. And then again, you expect here pressure to be high here. So what you do now, you accelerate in this direction, then you decelerate in this direction, because now you're moving against the gradient. Pressure is low behind and is high in front, right? If you're in an ideal fluid, everybody happy, you know. I was like 6, and I had an older brother, which also later turned to be a physicist. And there was a big pit in the Earth. He said, if we run down, then we'll have enough kinetic energy. He was probably 12, right? And I was 6. We have enough kinetic energy so we can run up. And of course, we ran down, and then he ran up, and I was, of course, stopped midway. Because you dissipate, right? So now if you imagine the particle which comes very, very close, and it's already inside the viscous boundary layer, that it undergoes friction. And when it comes moving here against the adverse pressure gradient, at some point it cannot move further. And what it does? It separates. Who said it separates? You are the first candidate for the book. Now, if it moves like this, then also fluid moves like this, but then here, again, here large pressure, here low pressure. The fluid would move like that. And we create a vortex. Remember yesterday I told this anecdote about this people who polished a cylinder from outside tried to get rid of pulsation in the force. And another genius in the same, and of course this German, and I'm talking about, was of course Planck. And the guy who understood about these vortices, and they are one by one are separated, and it gives you pulsation as a force, was his PhD student von Karman. That's Hungarian, okay? Austro-Hungarian. So what actually would happen is that you create a separation of the boundary layer, which totally changes the flow in the whole space. That's a non-trivial anomaly. A very tiny viscosity, however small. When viscosity goes to 0, this separation point stops depending on viscosity. And your resistance essentially determined by the radius of this. That's where you create resistance. You see? And that essentially tells you that there is something much more non-trivial in multidimensional flow as opposite to a simple case of Burgers where you just create a single shock. So you have a viscosity which is a small factor in front of the highest derivative. It changes flow in a tiny area, but you have a nonlinear equation, and this nonlinearity carries it forever and create a wake. This is called wake, and this is called separation. It's not exactly constant. Something happens around 10 to 5. Let's now try to, again, imagine intuitively what kind of can happen at a pretty large Reynolds number so that the resistance drops. Resistance drops, what do you think it tells you about wake? Is it getting more narrow or more wide? More narrow. So why the hell, as I decrease my viscosity, or increase my U, if you wish, this separation happened not here, but here. Absolutely, absolutely. So it's by the way Eiffel, the guy who built Eiffel Tower. He did well, not, I always thought that he built the tower to drop balls and measure their resistance. It turned out no. Okay, so Eiffel did the experiments and discovered this phenomena that Prandtl explained it. So what happened is that when you reach sufficiently large Reynolds number, this is getting unstable. And this is a true to God instability. You remember when we were talking about it? We said that this flow is linearly stable. You really need to disturb the boundaries to get a turbulence inside. This is now flow with curved streamlines. It's definitely getting unstable. So why the hell is the turbulent boundary layer separates later than the laminar boundary layer? What your intuition? Yes?
There's more momentum transfer from the outer fluid.
Absolutely. It's called entrainment. A turbulent boundary layer is thicker. So it has more inertia. And it carries more momentum and it separates later because what it needs to do, this inertia needs to overcome this adverse gradient between this minus and this plus. So this gives you this drop in resistance, which more or less you can see for soccer players can, I mean, really great, can really use it. Because when you want to shoot a ball over, when goalkeeper comes unreasonably far from the goal, then you could shoot the ball over it. And as your ball moves, so just imagine, like there is a goal, there is your goalkeeper, and you're trying to do it like this. But you want it to be like this. What really happens is that, of course, as it moves, it slows down. As it slows down, it moves in this direction. Its Reynolds number decreases. And at some point, its resistance sharply increases, right? And so it kind of, it slows down even more. And if you add to it also rotation, so you make it rotating, you add Magnus force, it could be a really very sharp trajectory down. And on some high levels, they really teach you how to do it. Okay, and this is exploiting the drag crisis. It tells you, by the way, that the soccer ball, which is the size is approximately 10 to 4, 10 to 6 Reynolds number. More or less, it lives in this interval. Okay? Good. So I want you to look at it, meditate, and see if you have any questions. Yes, Vlad. It's a finite domain statement. What is actually we're talking here, and it's really important. Yeah, the wake is infinite because you can prove a theorem. Anything finite, if you have your vorticity, and now notice, this is somewhere that what at the first lecture Berenger defined you. A turbulence is this where vorticity lives. There is no vorticity here, it's all potential flow. Everything which in the wake, it what comes out from boundary layer, it has vorticity. So this now, if this region is not infinite all the way to Chamonix, then you can treat it as a body, and you get back the paradox of it. So it's really important that wake give you this final thing, because it's a wake. It's change flow forever. Moreover, and I'm not going to talk about it, but if you look in the book, it changes flow over here too. But this is something, because it creates a finite deficit and it needs to compensate it. So this is really a very beautiful example, which we still cannot compute. But first of all, we can measure, and we can put on a computer. And when I was a PhD student, I tried to get this angle. I thought it is computable. Well, analytical, no. I don't think it's computable. I want to look at it and see if you have any questions, because from here, we'll start moving inside the wake. That's where turbulent lives, right? Questions? So you're happy? Yes.
So I followed you when you said that the stagnation point, the pressure is high, the velocity low. I followed you where you say that at the top of the sphere,
a wake changes pressure completely. What I've actually shown you by this pressure argument that you cannot without wake. So if you have a dissipation which slows down your fluid particle inside the layer, you cannot reach the stagnation point which is behind. And so wake completely changes the whole thing, right? And what is most important is that this wake is where vorticity is non-zero. Because when you pass near any solid body, you create this type of velocity profile, right? And this is vorticity. Right? Vorticity is a dvx over dz. Vorticity is the rate of rotation. So you see, and this is why sometimes physicists and engineers say that turbulence is where vorticity lives. That's where turbulence lives. Okay. Good. Now, of course, for me, as a physicist, turbulence is not where vorticity is. My definition is completely different from Berenger. I say turbulence is a far from equilibrium state of nature, or is a state where many degrees of freedom deviated from equilibrium. Those degrees of freedom could be spin waves, for example. Right? So I treat turbulence from the perspective of statistical physics and not from the perspective of fluid mechanics. But then again, it's a different perspective of different disciplines. Good. Now, what I want to, first of all, this C going to unity tells us that, of course, Newton was right. This is the force which acts on a body for sufficiently low viscosity or for sufficiently large size or large velocity. Okay? And you need to be Newton, you know, who actually also introduced viscosity. Now, if we are comfortable with this, I really want to move into turbulence and look into the following situation. Imagine that we take a closed volume, and in this closed volume, I don't know, I have this sphere or I have a fan, I don't know, like rotating, moving over and over, right? So it moves, and it moves the wake behind it, namely that it kind of impacts momentum into more. You remember that Newton got his formula just asking how much momentum you impact per unit time. So you just move, you see a standing fluid, you give it momentum. Then you move, you give momentum, you give momentum. Now this is a force. Let's take this force, which is rho u squared r squared, multiplied by velocity. It would give us power. How much power, how much energy per unit time I impact into this. Let's say this is a fan, so this is the air in the room. And I divide it by rho r cube, which is the total mass. So this is the energy, or rather power per unit mass. That how much energy, kinetic energy of a fluid motion I impact per unit mass. And because it so happened that this is independent on viscosity, then this is apparently also independent on viscosity, and it's u cubed over r. And then I ask myself, so what will be if I'll take this room? I don't see any fun. So anyway, I take some closed volume and start a body moving there. It would impact more and more and more and more kinetic energy. Would it stabilize? Or kinetic energy would grow and grow and grow and grow. And I'm just moving. I'm moving, I'm doing work. I'm involving the air in motion. I move this direction, then I move that direction. What's your intuition? So what you're saying is that the kinetic energy of the air at some point stopped growing. What would be growing is the temperature of the air in this room. Everybody agrees with this. This is, by the way, everyday intuition. Then when we switch on fan, we don't expect that at some point there will be a hurricane in our room, right? we do know that if we switch a fan and not air conditions, the air will be hotter. Because what essentially we are telling is that somehow all this energy that I put into kinetic macroscopic motion of the air on this coarse grained scale, as you've seen in the first lecture, somehow gets into molecular motion of molecules. And this rate with which it does is totally independent on viscosity, which is my molecular scale. So I'm saying, okay, you remember that viscosity is Vt times L. Let me, I don't know, shrink, temperature that, and it's independent. So how it could be that the rate of dissipation of my kinetic energy into heat is totally independent on the properties of molecules over there? You got the book. Or you read the book, maybe you don't need it. Does this answer make sense? Why? Yeah. Cascade means that you kind of have a pipe in Fourier space, right? So you put your energy at large scales. Let me now draw a Fourier K. So this is your 1 over R, right? This R. So you put your energy here. So there is somewhere a scale which is proportional 1 over nu, right? You remember this, the size of a boundary layer, whatever, some viscous scale. So what happens is when your nu goes to 0, this kind of goes. But it acts like a pipe. Okay, so the pipe will be like this, or the pipe will be like this, or the pipe will be like this. It still carries the same amount of energy through scales, which is an idea of cascade. It's again very close to bullshit, as close as one gets. So there is no single formula here, just a mental picture. But what so happened is that at about the same time when people were doing this measurement, some other people, and this time in Great Britain, did another measurement. And he actually measured a diffusion. You know that 10s and 20s was, I mean, the Perrine, Langevin, that's here, I mean, the continent, people did Brownian motion, atoms, and then everybody was talking about diffusion. Everybody was so excited about this Brownian motion because the first time people proved that atoms exist. You can actually measure characteristics of the atom. And then on another side of an English channel, a guy named Richardson wanted to do atmospheric diffusion. I put dates because dates are important, right? Because you are scientists yourself, so you know how it's important that something was done this year and something was done just a year before. So what he did, he released a particle, balloons, seeds. He experimented with very different things at some distance and let them evolve in a wind, in a turbulent wind. So they were moving, and then he measured, with not a great accuracy, the distance as a function of time. And he released many such pairs and observed many such pairs and measured r squared average, and because address over what average over what, in this particular case it is average over ensemble of a seeds. You just take it, throw them away, then you look at different pairs and you measure how they actually evolve, and you try to average keeping more or less the same r of 0. So you consider different pairs which at time equal to 0 started more or less at the same distance, and you release them. Okay? What he expected to find as a function of time? A linear law. He expected to be a diffusion. what he found, you probably all know, he found the Richardson law, which means, yes, we now call it super diffusion. So he found out that these particles in a random turbulent flow separate much faster than you would expect. What is the coefficient here? It has a dimensionality centimeter squared per seconds cube. I already erased. Let me remind you that epsilon, which is power per unit mass, was u cube over r, which has a dimensionality centimeter squared per second cube. Any connection? Let's see. If I have r squared behaving like t cube, I can again hand wave my wave into saying where it comes from the following way. I can say r behave like t 3 halves, right? dr dt behaves like t 1 half, right? Behaves like r 1 third, right? Are you with me? Good. But that's delta v, right? Remember in the first lecture we were saying that ddt of the distance between 2 points in the flow is delta v. Okay? So what it tells me is that if I would measure in some sense, and we spend this lecture and the next two discussing in what sense statistically really, but so far it's just hand waving, right? There's no angular brackets, no statistics, just I would say where it could come from, particularly what stands here is epsilon, is this would be, and then you hand wave your way into this argument saying, I mean, look, you remember this cascade idea? It tells me that in turbulence, my energy impacted on a large scale. Let's say I have a temperature gradient which drives wind. Any horizontal temperature gradient immediately produces wind. The typical energy at a given scale r is delta v squared. Namely that if you can mentally think like you have 2 points with the distance r, so there is a vortex of this scale. And the difference between this and this point, it's more or less this vortex was contribute, right? If I would have some large vortex like this, then velocity here and here would be approximately the same. And if I would have small vortices here and here, they would contribute velocity differences which are uncorrelated, and this would be diffusion, right? So what I suspect is this super diffusion comes out of somehow vortices of a scale comparable with the distance. So I may say that delta v squared is a typical energy at scale r. It's a very hand-waving argument. Now I want to estimate the rate with which this energy flows through this pipe in Fourier space or through these scales in R. And what is good about fluid mechanics is that if you want to rate how many energy per time, you need a typical time. And fluid mechanics is mechanics. Time is always distance divided by velocity, right? So what I need to put here to get a typical time, a turnover time of the vortex, or time of lifetime of a vortex, or a time of energy transfer through the vortex, I need to take the scale, which is, tell me what to write here. It's a distance divided by velocity. What is the velocity? I am at this scale, right? There is no mean velocity. No, No, just delta V, the same delta V. What I'm saying, if I have a vortex with a delta V on a scale R, this is its typical energy, this is its typical turnover time, right? So this, I would say, is my typical energy transfer rate, which happen to be delta V cube divided by R. And I want this to be independent on R. And this immediately gives me this law. You see? So the superdiffusion of Richardson is essentially a demonstration of a cascade in this atmospheric turbulence. 100 years from that, we never, ever were able to repeat it in the lab. With a huge effort spent into it. We're almost there, but it's happened to be very difficult. Really cleanly absorb this data. When you look at the data of Richardson, I can put many lines there. And again, the better you do experiment, the more confused you usually are. And this first simple experiment gave us this 100 years beautiful turbulence theory. But 100 years after this, experimentally still an open question, what are the validity limits of Richardson law? Okay? Yes? Of course not. I'll talk about it. Maybe next lecture. Okay? And again, it's different in 2D and in 3D. When you have direct cascade and inverse cascade. It's very, very different. Okay? But still, and that what somehow tells you how science sometimes moves. You do something which is not exactly right, but it's true. There is some deep truth in Richardson, even though experimentally, and again in the same Prandtl lab, which was a Bodenschaft lab, etc., people still are working and do very many beautiful, and it's very difficult really to make it very cleanly. But on this level, on this hand-waving level, it all fits nicely. This constant, which tells you that the body acts on a fluid with a force, or fluid acts on a body with a drag, which is independent on viscosity, which gives you that it corresponds to a constant rate of energy input. That's when this body moves, that leaves this kinetic energy behind. That's where Richardson law lives, right here, right? And then we see this law, which tells you that Z delta V cube is epsilon r. First of all, it's a statement, if we now really say what it actually tells. It tells the following thing. So you take distance r. That was, by the way, a Lagrangian argument. When Alan Pumir will teach you Lagrangian and Aurora next week and also this week. So this was an argument about particle moving over there, right? But this was already an Eulerian argument, namely, if I take a given distance, I measure average velocity difference cube, average at a distance r, it's somehow epsilon r. So this is a statement which is totally Eulerian in a sense that you just look at your flow, pick any pairs of points at the same distance r, measure velocity difference. Average velocity difference, of course, is 0. Your flow on average does not shrink and it does not expand, right? Average third moment is proportional to epsilon r, but it also has a sign, right? It's not delta V squared, which is always positive. What a sign we expect here? Huh? Minus. Well, you know that it's minus, right? Why? Well, of course, we're now about to derive Kolmogorov Kolmogorov always claims that he never heard about Richardson. His student, who derived a kind of analog of it, Obukhov, at the same year, actually knew about Richardson. And I always, unfortunately, Kolmogorov was already ill when I was a student. I always wanted to ask Obukhov about it, and somehow was too shy about it. Now they're all dead, and I don't know what's the truth. I suspect that he knew about Richardson. So Kolmogorov derives this, which we're about to derive analog of it, and it's a minus. What this minus tells us qualitatively? So again, delta V on average is 0. Delta V cube is negative. What it tells you, sometimes it's called skewness. It tells you that your probability distribution, and now we're starting to talk, okay, so this is, we memorize this picture, right? I can erase it, but we always have it in our hearts, right? Because this is that's how engineers view turbulence. That's where it comes from, right? So now, let's ask, so on average, it tells me that negative and positive are more or less the same, but the delta V cube negative means what? Means that when there is delta V large over here, right, this probability is larger. So it's kind of something like this, and it's more like that. I'm kind of exaggerating, but it's kind of skewed, right? Or it tells you the following thing, that if you take at a distance r somehow large delta V, then, and by the way, as we'll derive, that would be longitudinal, namely projected on this direction. It tells us that when there is a large velocity difference, it's negative, kind of in this direction. What physically it tells us? Yes? It tells us that on average, it's 0. Namely, if you ask what is the probability that it's in this direction or in this direction, the same. But now you condition. You say, what is the probability that this is in this direction or in that if there is a big velocity difference? And you say, if it's a big velocity difference, then it's more probable that it would go this way. Namely, all this energy would go to smaller scales. That's the direction of a cascade. In 2D, when there is an inverse cascade, this will be a positive sign here. Okay? So when there is a big vortex, then on average, this energy would go towards smaller scale, and there's a direct cascade. That means that energy would go to smaller and smaller scale. And of course, you can derive a different correlation function like delta VL times delta V modulus squared. There are a lot of geometry over there, but essential physics in this sign is a cascade direction. And again, you switch time, right? And then your epsilon changes sign, right? Okay? Good. Questions? We're moving pretty fast. That's why I slow down some. I'm doing only elementary things, but relatively fast. So I want you to slow down, and we're already, talking an hour and 10 minutes, so you must be pretty tired. So I want you to take a deep breath and understand what we actually did. From a friction factor to a cascade, then to a Lagrangian motion, to superdiffusion, which suggested this law. And so what we essentially did, we interpreted this law. There were no derivations so far. Now I start deriving, and then we'll go for a break. But so far, this is interpretation. So I interpreted Richardson data, this data, as a cascade. Okay? Questions? Happy with this? Happy? Good. Could we derive it? Well, I just told you Kolmogorov did. And so let's derive it. and I'll give you 2 minutes to close your eyes and relax. It's much easier to talk hour and a half than to listen, right? So I am in a better shape. Relax, relax. Close your eyes. Think about water running. Meditate. You did it for yeah, yeah. I just want to show it briefly for burgers because then I will be returning. Okay, so because I'm lazy and I'm not going to do a real job, so what I want to do, I want to take burgers, add a random force to it, okay, and I assume that this force is random function of x and t, and it's Gaussian, which means that it has a zero mean, but when I have it at it has some, let's say it's white in time, and it has some, and I assume that this chi is a function of x minus x prime, it has some typical scale a. Okay? So what I'm now gonna do, I wanna look at the u1 minus u2 squared as my delta v analog, and I assume that x12 is much, much smaller than L. But also I assume that this nu over here, so it's much, much larger than something related to nu related to some u. Okay? And okay, and now I wanna just take this, do ddt of u1 minus u2 squared, and it's very similarly to what you did for third, where it's here it is. And this is of course 0 if I'll take average, so I consider a stationary situation. So I would have 4 u1, and here I substitute u1 u2 is u1 u1x minus nu u1xx minus plus f1, and then I will do the same with 2u1 u2 u2x minus nu minus u2 xx plus f2x and minus 2u2 . I want to do it because I really want to call your attention to one substantial element over here. So there is a respective term where is u2, 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 but I just put here a factor 2 so that it's kind of the same because I'm assuming translational invariance. And this will be kind of average, right? So now what I will assume that when I do here a product u1 f1, it's a power. It's my force times velocity, and I assume that this power is this epsilon which I impact into the flow, right? And when I look at this average of this one, it would give me nu ux squared, which would be again epsilon because it's a dissipation. And I assume that they are equal, namely if there would be u1 squared, so on average I impact as much by power as I burn by viscosity, we already discussed, right? So in this term, I mean this times this and times this would just cancel each other, and this is a total derivative, which means that the average of it is 0. But it's differently over here, because here I have u1 and here I have u2, u2, u2. But what I assume now that u1 f2 is still approximately equal to epsilon because my force is a large scale and my x1, 2, 0.1 and 2 are very close relatively to the correlation scale of my forcing. Right? So this is approximately epsilon. But when I look at this, namely the correlation between u1 and the Laplacian of u2, they are uncorrelated because this distance is larger than my viscous scale, and the viscous scale is a scale in which my gradients are correlated. Okay? So I'll be neglecting this but taking account this, and by the same token I'll be neglecting this and taking account of this. So what I will be left with is that there will be a term like this. Let me write it here. It's u1 ddx u2 squared over 2 with a factor 2. But I can put u1 in between because it's a derivative with respect to 2, right? And by the same token here, I would have d of dx1 u1 squared over 2 u2, right? Now I am saying that in a translationally invariant situation, I expect all my correlation function only be functions of x1 minus x2, which means that any derivative with respect to x2 could be replaced by the minus derivative with respect to x1. Okay? I really want you to see this kind of elementary steps, because in multi-dimensions there are some things. So what I now have out of here is the following thing. That I would have d over dx2, and here will be u2 squared u1 minus u1 squared u2 divided by by 2, and from here would come 4 epsilon. Now when I look here, I say that let me add to it u cube 1 divided by 6 and minus u2 cubed divided by 6. It's 0, because on average d dx2 of this is 0. This is something which is independent. This is a single point average, and it's independent on coordinate. So what stands here eventually would be 4 epsilon plus d dx 2 u1 minus u2 squared over 3. Right? And it immediately tells you that u1 minus u2 squared mean value is minus 12x12 epsilon. Okay? So this is a very simple, and yet this is an important derivation. And first of all, it also tells you how the direction of a cascade come here. You see what I assumed? I assumed that I have a large scale forcing and a small scale dissipation. So this my epsilon came from this term, right? But when you do it in 2D, you do it in an opposite way. You assume that you have a small scale forcing, then this term would be 0. But your dissipation is something like uniform friction or something, so whatever stands here for dissipation would be correlated with this. And then you get an opposite sign over here. Right? It's another way to see, I'm not repeating this computation, but it's kind of another way to see. And of course, when you do it in a 3D incompressible fluid, you would get a geometrical factor, and essentially, if you do it in d-dimensional space for incompressible fluid, you do it delta V longitudinal cube. This is a general result, but of course when you put d equal to 3, this is 4 over 5. When you put d equal to 2, you need to change sign of epsilon, because then it will be plus here. So this is called a flux law. Or Kolmogorov 4/5, or this is Burger's 12, etc. It's basically very interesting to. I always ask myself, can I get this 12 without computations? Like, because it is like this 12 which is here is, but I didn't. So maybe you can get your intuition around it. Okay, so let me now wrap out what we did in these two lectures, because tomorrow we start destroying it. Questions? Essentially, it tells you the following thing. Forget about everything. You have this equation, right? So du dt is f, and f is a white noise, right? Just write u is an integral of f of t prime dt prime. Multiply, this is u of t, right? Multiply it by another u. You get integral of f of t2 prime dt prime, right? So, and then this is delta correlated. So in a sense, when you compute mean value f times u, then you need to compute, where is it? This is your u of t. It's f integral dt. Make it time, make it f of t, and average, right? And this is a delta function of t minus t prime. So it immediately comes as a, this is epsilon, right? This is the magnitude of your forcing. Okay? So, well, you can do it for finite correlation as well, but this is kind of a simple way. But generally, force time velocity is a power. That's how much power you impact. Yeah. What I actually did when I was deriving here, I was arguing that because I consider direct cascade, U1, F2 are still correlated. Because 1 and 2 are too close. F is a large scale forcing, right? And this 1 and 2 points are still within the correlation radius of the force. So this U1, F2 is about the same as U1, F1. That's, and here I'm making a statement, direct cascade, large scale forcing. Okay? More questions? Okay. So now what we know for sure is that our turbulence does the following thing. It dissipates independently on the dissipation factor. And then we know third moment. Third moment is linearly proportional to the distance and to the epsilon dissipation rate. This basically a consequence of the fact that our integral of motion is delta u is u squared, right? So you remember, I always want you to remember this simple argument. The students of Obukhov used to joke that Obukhov discovered all thirds law. There is 4 thirds, 5 thirds, 7 thirds law for pressure, etc. And of course, these thirds come out of this, right? So you have quadratic invariant, and your time is inversely proportional to your velocity. So your velocity is always here in the third power, right? And then you can do different things. So now we know that delta V cube, what can we say about delta V squared? Or delta V in the power n? That's what we'll be doing next 2 lectures, but we start now, at least we pose the question. Well, dimensionally, we may say that this must be like epsilon r 2/3, which you say that this is an integral of epsilon k dk of a 1 over r, then that would be k minus 5/3, which is a famous Kolmogorov spectrum, the most famous wrong result in fluid mechanics. Does it make sense? And if it does, why? And if it does not, why? What kind of assumption we make when we say something about other moments by knowing only one moment of velocity? Gaussianity is a very particular case, and we know that the statistics of velocity could not be really universal. It depends what is your forcing, right? Like we used to joke about, let's say we consider toilet turbulence, right? That people come in the toilet every minute and somebody does this. So people come once an hour. You do. It's still turbulence. It's high Reynolds number, but it's a very different statistics. Okay, so let's talk about last 2 minutes that we have about the whole probability distribution. What is the probability of having delta V? Let's say this would be a longitudinal projected on this distance at a distance r. It's a function. We assume isotropy. Now I'm starting talking like a physicist. Namely, I'm talking about symmetries. Okay? I really want you to see which hat I'm wearing. Now I'm not an engineer. I'm a physicist. I'm talking about symmetries. I assume this to be isotropic. Then this is a scalar. But this, generally, initially, this was a vector, and this is a vector. And there are very many different tensorial and scalar characteristics which I can make out of them. I said, okay, let's forget it. Okay, so this is a scalar, this is a scalar. What symmetry properties I expect from this probability distribution? That's what we'll be talking about. Any suggestion in the last minute? Yes. Scale invariance is one. What other invariances we can make? I mean, what transformation we can make? Well, you run out of your imagination. What you can do with a fluid? Scale invariance means I can take a picture of a fluid flow and enlarge it or shrink it. What else? Translational invariance, which is essentially already assumed here because it's a distance between points. So translational invariance already done, but already done, it's a scalar. Time, of course. Don't forget, it's mechanics. Mechanics is space and time. So what with time I can do? Time translation does not matter because already differences. Time reversal. Let's start from this. We have half minute. Can we say that it's time reversal or it's definitely not time reversal? Time reversal means V turns into minus V. That's it. That's what if you make a movie backwards, that's what velocity changes sign. Do we know for sure that time reversal is broken, or we know for sure that time reversal is there? Yes. Absolutely right. First of all, the very fact that I have a cubic does not matter which sign, right? Positive, negative, does not matter. If my delta V cube is non-zero, but it changes sign when I change time direction, that immediately tells me that it's time irreversible. And of course, turbulence is about dissipation. Okay, that's the end of second lecture, and tomorrow we'll start right here. Okay. Thanks for suffering. It was a long lecture. So I